Fourier series possesses various properties. Let us look at them one by one. The first property that we are going to look at is the simplest one, that is called as a linearity property. Let's suppose we have a signal, let's say x of t, having the Fourier series coefficients as ak. Let's have another signal, say x2 of t. So let the first signal be x1 of t with Fourier series coefficients as ak, and let x2 of t be another signal whose Fourier series coefficients are, say, bk. The linearity property says that if we give a linear combination of the inputs, we get the linear combination of the Fourier series coefficients at the output. That means if we have this linear combination of the inputs, that means, say, a times x1 of t plus b times x2 of t, that would give you the output as a linear combination of the Fourier series coefficients a times ak plus b times bk. This property is called as a linearity property of Fourier series. This property can be proved from the definition of the Fourier series coefficients. You can see that the Fourier series coefficients are given by ak, that is equals to 1 upon over a period, that is capital T, x p of t e to the power minus jk omega naught t dt. Now as we are giving a linear combination of the inputs, that means xp of t here is a times x1 of t plus b times x2 of t. You can see that as this integration can be splitted linearly over this summation, we can easily see that the output is also going to be a linear combination of the individual Fourier series coefficients. Let's look at another property. The second property that we are going to look at is what is called as a time shift property. The time shift property says that, let's suppose if we have a signal, say x of t, with the Fourier series coefficients as ak, then the shifted version of the input signal, let it be x of t minus t naught, where t naught is the amount of shift, its equivalent Fourier series coefficient is going to be the same ak being multiplied by an exponential given by e to the power minus j k omega naught t naught. This is called as a time shift property, which says that if I shift the input signal by, say, an amount of t naught units, the Fourier series coefficients are going to be the same. The only change will be there in the exponential term. A factor of exponential will be getting multiplied to the Fourier series coefficients, and that exponential factor is given by e to the power minus jk omega naught and the amount of shift that has been incurred in the signal. So this t naught is going to be this t naught, that is the amount of shift in the original signal. This is called as a time shift property. This property again can be proved from the definition of Fourier series coefficients. We know that the Fourier series coefficients are given by ak, the same formula here, So this one here. So now instead of xp of t, we have this modified xp of t, that is t minus t naught. Therefore a case will be given by equals to 1 upon t integration the x of p t minus t naught e to the power minus j k omega naught t naught dt. Now that is given by, now I'll make a change of variable here. I'll replace t minus t naught by say t dash. This implies that dt is equals to dt dash. This gives a k equals to 1 upon capital T integration x p of t dash e to the power minus jk omega naught, and t naught is given by t minus t dash dt dash. So that is equals to, this is equals to 1 upon capital T. So I'll take this, I'll take a factor of e to the power. You can see that here the factor e to the power minus jk omega naught t can be taken outside just because this integration is with respect to t dash. So this complete factor e to the power jk omega naught t can be taken outside. That is going to give you e to the power minus jk omega naught t naught being multiplied by 1 upon capital T integration over a period x p of t dash e to the power minus jk omega naught t dash dt dash. We can see that this factor here in the bracket is nothing but the formula to calculate the Fourier series coefficients. So this new AK, let me call that as AK cap, just because this is the modified Fourier coefficients, the Fourier series coefficients of the shifted version. So this complete term is AK capital dash. So that is nothing but an exponential being multiplied by the original AKs. What does this mean is, if you have a signal x of t with the Fourier series coefficient of AK, if I shift the same signal by an amount of t naught, the resultant Fourier series coefficients are going to be the same, except with a multiplication factor of e to the power jk omega naught t naught, and that's what we have proved here. So this is the proof for that. You can see that the factor e to the power is getting reflected here. Let's look at third property of Fourier series. Another property that the Fourier series possesses is what is called as a time reversal property. That says, so let me write that as time reversal The time reversal property says that if I have a signal x of t whose Fourier series coefficients are given by AK, then the Fourier series coefficients of x of minus t is given by a of minus k. So you can see that if a signal is flipped over time, then the Fourier series coefficients are also getting flipped over kth axis. This we can prove again from the original equation for the Fourier series coefficients. So let me prove that. So proof, if you have the x of t being represented as equals to summation for k ranging from minus infinite to infinite a k e to the power jk omega naught t, then x of minus t is given by summation over k from minus infinite to infinite a k e to the power minus j k omega naught t, and we can see that this is nothing but, I'll make a change of variable here, so I'll replace this k by minus k. So that is going to be, if I replace this k factor by minus k, so just because I have a minus sign here, if I replace k by minus k, this term is going to be similar to this term, but the only change here would be summation. So k is going to be equals to minus infinite to infinite a of minus k e to the power j k omega naught t. So this is going to be the Fourier series coefficients of the shifted version, that is new ak, or this new ak being for x of minus t. So this is the proof. You can see that the Fourier series coefficients are also getting flipped over the kth axis if we flip the input signal over time axis. This is very important property, and this actually helps us to derive few other related properties. Next property that we are going to prove is what is called as, write that here, the fourth property that we are going to prove, that is called as time scaling property. The time scaling property says that if I have a signal x of t with a Fourier series coefficients as ak, then the Fourier series coefficients of the scaled version of the input, that means x of say alpha t, here we are scaling the input where this alpha is a positive real number, then this signal, the Fourier series coefficients are going to change. Now we need to look at what are those Fourier series coefficients going to be. Now the Fourier series coefficients, let's look at what are going to be the Fourier series coefficients. So let me write that. So Fourier series coefficient x of alpha t is going to be summation k ranging from minus infinite to infinite ak e to the power, now instead of t we have this alpha t, so we have j k times omega naught alpha t. So this is equivalent to summation k equals to minus infinite to infinite ak e to the power j k alpha times omega naught times t. Now what does this mean? This means that the Fourier series coefficients that we have obtained, that is ak, is now going to change. The signal that was periodic with the angular frequency of omega naught is now periodic with the angular frequency of alpha times omega naught. So that means that if the signal, the original signal, if it is periodic with the period of capital T. Now it is going to be periodic with the period of T by alpha. So let me write that. If for omega naught implies T equals to 2 pi by omega naught. Now what is the T for this, the modified one? So for alpha omega naught is going to be T by alpha, so time period is going to be equals to 2 pi by omega naught times alpha. So this modified, you can say that this is the modified period, let that be T dash, and that is going to be the modified version of the original T. So this is capital T, and that gets scaled by this alpha. So what does this mean? If I have a signal x of t that is having the Fourier series coefficients as ak, if I scale the input signal by a factor of alpha, the frequency is getting scaled by the same factor, that is alpha. So that means that the original signal that was periodic with capital T as a period is now periodic with a new period, that is T by alpha. This is called as a time scaling property of the Fourier series coefficients. Let's look at some other properties. The fifth property that we are going to look at is what is called as a multiplication property. The multiplication property says that if I have two signals, say x of t, x1 of t having the Fourier series coefficients as ak, let x2 of t be another signal as Fourier series coefficients as bk, then if I multiply the input signals, let's say x1 of t times x2 of t, then the resultant Fourier series coefficients are going to be the convolution of ak and bk. This is the property what is called as a very important multiplication property. If I multiply two signals, two periodic signals in the time domain, then the resultant is the convolution of the Fourier series coefficients of the individual signals. Should note that here x1 of t and x2 of t are both periodic with the same period. So let me write that. So here both are periodic with period capital T. So if I multiply those two signals in the time domain, we are going to get the convolution of, or to be very specific, it is going to be the discrete time convolution of the Fourier series coefficients. This is called as the multiplication property of Fourier series coefficients. Let's look at another property. So sixth property that we're going to look at is what is called as a conjugate symmetry property, the conjugation property. The conjugation property says that if I have a signal x of t with the Fourier series coefficients as ak, then if I take a complex conjugate of x of t, say x star of t, then its Fourier series is going to be a of minus k times complex conjugate. So this is very simple property that says that if I take the complex conjugation of the input, I am going to get the complex conjugate with a flip over the Fourier series coefficients. Now, using this property, we can derive some other auxiliary properties. This conjugation properties helps us in analyzing the even and odd signals. Now let's suppose, as an extension to this property, let's suppose if I'm having an even signal. So let me break this down into two parts. So let's have this, let's make use of this property to derive some other properties. So I'm saying that if the signal, the input signal, if x of t is real and even, I'm assuming that, let's suppose if this x of t is real and even, what is going to be the effect on the Fourier series coefficients? We know that if a signal is even, we say that x of t is going to be equals to x of minus t. So that is from the definition of even signal, that the signal and its flipped version are going to be equal. So that is the definition of an even signal. So if the original signal x of t is an even signal, and if it is real, then let's see what is going to be the Fourier series coefficients. We know what is the effect that happens as we flip the signal. If we flip the signal, that means if I have x of minus t, as we have seen from here, if I flip the signal from the previous property, we have seen that if I flip the signal, we get the Fourier series coefficients also flipped. So we have this as ak b equals to a of minus k, and as we know that the signal is real, that means a k and its complex conjugate are going to be the same, with a change in the inversion of the Fourier series coefficient axis, that means the kth axis. This property is actually the effect of the signal being real, and this one is the resultant of the signal being even. Now, what does this mean in totality? Together, this means that ak is going to be equals to ak star. So this is true for the signal if it is even and real. What does this mean is, if the input signal is real and even, the Fourier series coefficients are also going to be real and even. You can see that from this expression that the Fourier series coefficients are also going to be real and even. So this is very important conclusion that we are drawing it here. If the input signal is real and even, then let me write that this is going to be real. The Fourier series coefficients are going to be real and even. Now let's see what happens if we take input signal x of t as real and odd. So if I have this input signal, let's say if x of t is real and odd, we can see from the definition of odd signals that x of t is then going to be equals to minus of x of minus t. So that is from the definition of odd signals. And for real signals, of course, AKs are going to be equals to, so let me define this AKs for this odd signal. You can see that for odd signal this is going to be equals to, AK is going to be equals to minus of A of minus K. This is the effect from the property that we have used for the flipped signal. If I flip the signal, the Fourier series coefficients are also flipped over the kth axis, and just because the signal is odd, we have this minus sign here as it's getting reflected here. While the signal is real, we have the other properties that AKs are going to be equals to AKs complex conjugate, A minus K's complex conjugate. Now from both of them we can see that from these two individual properties we can see that in totality what does it mean is that this AK, let me write that, this AK is going to be, this AK is going to be equals to minus of AK star. So let me emphasize this. This says that AK is going to be A of minus K star. Now what does this mean? If the input signal is real and odd, the Fourier series coefficients are going to be odd and they are going to be purely imaginary. You can see that this Fourier series coefficients and its complex conjugate and the negative of that, if they are equal, that means the Fourier series coefficients are going to be imaginary. And of course, because of this minus sign, they are going to be odd in nature. So let me write that it is going to be imaginary and odd. This is very important property that we are seeing here. If the input signal is real and even, the Fourier series coefficients are going to be real and even. If the input signal is real and odd, the Fourier series coefficients are going to be purely imaginary as well as odd in nature. We shall look at some more properties in the next module. See you then.